So here I made some note. I said note the high number of model parameters, and even the large degrees of freedom. So this one is a positive, actually not negative. So I think I made a mistake here. The larger your degrees of freedom, the better your model. Okay, so I ignore this one. It's a key thing here. So if I count, I have, because for the residual, if I have 60 degrees of freedom, means I can change. I can make changes to 60 different data points. So the higher this one, the better your model anyway, not the reverse. This one is the one that relates to your sample size. Okay, usually the rule is to have the sample size to be 10 to 20 times the number of parameters. So that's what I find in structural equation modeling literature. In normal statistics literature, we say you should have about five times the number of parameters. Okay, in normal statistics, we say let your sample size be about 5 times the number of parameters. You get that? In structural equation modeling, I see the proposed 10 to 20, and probably to do with these covariant structures and so on. So this one, I think this one, as I said, you can leave out this one. I think I wrote down some. I was trying to write something different from what I wrote. Here, this is not the problem. This one is actually good to have high degrees of freedom here.
Sorry, for what you meant by when the degree of freedom is higher, it's a better model, like better in which way?
Here. This degree of freedom is good because
yes, it's good. In what way? Like,
okay, like
what is good?
Let me take like a line. Remember, I said that if I take a straight line, if I have only 2 points, then I'll get perfect fit. So my degree of freedom here will be 0. If I take, because there's no other way of varying the parameter, the slope is going to be 1. If I take 3 points and I fitted a straight line, my degree of freedom will be 1. So it will be n minus the number of parameters. If I take 20 points and I fit a straight line, my degree of freedom will be 20 minus 1. 1 being the slope, which is going to be 19. So you see that the more the number of points I'm having in my data, the more the degrees of freedom.
Yeah, okay. Then I think I'm more confused because the way you explained the degree of freedoms, it doesn't match the line example you just give.
Okay.
Like in Excel, I get it. Like for each point inside there's only a degree of freedom for 1. But as another example, as you said, a linear regression of a few points, then why it is n minus 1? I don't really get it. I mean,
you see why it's happening here is that this is like fitting. This is like your regression with 2 points. For me to get to 225, I have 2 points here. So I can only change one of them.
Yeah.
You see that the sum must be this, so I can only change one. Now, if I extended this table and put another column here, okay, let's suppose we put another column here. Yes, no, don't know. Okay. Then immediately my degree of freedom will increase to 2 because I have these 2. I can put the third value here, say 3. Okay. Together they must sum to 25. So now I can change any 2 values and they will sum to 25. Down here, I will only have 1 degree of freedom, but across here, we'll have 2 degrees of freedom.
Okay. I see. So,
because if I'm coming down here, the total must be 30. So once I put 1 here, the next number here must add to 30. But if I come here and I put 3, by the time I put, let's suppose I come here, let's do this number here. We had here was what? Minus that. So that would not be minus that. That would be minus that, minus this one. Okay. So now you see that the 3 has changed. Because so I've just fixed this one. So you see that if I come here and say 4, so 6, sorry, see it's minus now. You see that? So I say 7. So that you a perfect fit for that one. I said 5 here, you see. So I can change these 2 numbers without changing this one. So I have now 2 degrees of freedom, 2 places where I can change and still get my total. But down here, down here, the total must remain this. If I change 1 here, this number will change. So on this row, I have two numbers that I can change and still maintain my 25. Here, I have only one number. If I change this number, this will automatically change.
Yeah, I mean I get it, like the calculation of this, because it's a sum. So conceptually, I just need to understand conceptually, because like in this example, the reason that there is a freedom of two is because of the model. The model is
Thank
the
you.
sum.
That's exactly it. So in our model, when we translate this to a statistical model, we used what we call the number of parameters in the model, together with our sample size, to determine the degrees of freedom. Okay, so it's a function of the number of parameters and the sample size. Here, it's not exact difference, because there are certain other parameters that are being computed in order to compute the chi-squared here that we are not seeing. For example, the covariances and the covariances and the variances within the parameter that we are not seeing here are all part of computing the chi-squared, and we add those to the model parameters and then subtract from the sample size to get our degrees of freedom here. You see that? So if there were no other calculations, if this was regression, then this number here will be 1210 minus 190. If this was normal regression, because there are no other parameters to be computed. Okay, then this number will be 1210, the sample size, minus 190. But because there are other parameters that are being calculated that we don't see here, they are taking those parameters, adding them all up, and then subtracting from 1210 to get your degrees of freedom here. Does that make sense?
No, I'm not that far yet. I'm just again, like conceptually trying to understand this. So like here, like you said, it's the degree of freedom is a function of the sample size and the number of model parameters. So if we go back to the Excel that you just created, so in this one, what is the parameter?
Okay. Model? Yes. It's good that you are challenging my concept there. Remember, I said that I use this to explain whether somebody understands it or not. I don't know, because I enjoy explaining with it. Now, the way statisticians define the word degrees of freedom was from this type of concept. So how much freedom do you have with your data? In those days, we used to have what we call sufficient statistics. So if I give you a sample of size n, whatever n is, and I want you to do certain calculations, I would say, what are the sufficient sizes for that? So if I wanted to find the mean, it's enough for me to give you the sum and the sample size. You know that the sum divided by the sample size will give you your mean. You see that? So if I want to find variance, I will give you the mean, or I can give you the sum and the sum of squares and the sample size. And with those three numbers, you'll be able to find your variance. Okay. So within that context, they also derive this concept here to say, how much freedom do I have in my numbers in order to estimate this? So they derive all of those using this concept, but they are derived using certain mathematical formulas based on what you're estimating and what you are testing. Okay. So I couldn't derive them for you just now without going back to maximum likelihood estimation formulas and so on to show you the number of parameters that are being used. But what I can tell you is that, in your factor analysis, the first thing that you know is that because you're estimating the covariance metrics, okay, the covariance metrics is being used there. So if I have t variables, then my covariance, so if I have, let's suppose these are my variables here, okay, my covariance metrics, I have 3 variables. So I will have 3 by 3. So the correlation between them, which is the number of variables minus 1 divided by 2, will give us the correlations, plus the variances will give me the number of parameters from that covariance matrix alone. Okay, just the covariance matrix alone. So if I have 3 of them, I will have 3 correlations plus 3 variances. That's 6 parameters. So I'll have 6 parameters coming from the covariances plus whatever my path coefficients are. All of these path coefficients will be added up together with their covariances to give me the total parameters that I'm estimating that are now used to find my degrees of freedom here. So it's a complex. It's not complex for somebody who write down the model to determine this number, but I couldn't just give you offhand to say it will give you this. So all the covariances that are being used in this model estimation, they will calculate, they will count them. All the path coefficients that are being estimated, they will count them. And any other function that you need to calculate this chi-squared, They will add them up and then subtract from n to get these degrees of freedom here. Okay. Does that make sense? They'll add up everything that you need in order to estimate, in order to calculate this statistic. Where's the statistic? Where's the chi-square statistic? Here. In order to calculate this number here that they say 193, they'll add up all the parameters they need, subtract that from 1210 to get this number here. Does that make sense? So they'll add up and say, I need 190 variances if these were path coefficients. I need 190 variances. I need 2 times that in covariances, which will give me, say, 3 something. That will give me about 400 and something. I need maybe another 2 times that in correlation. That gives me a total of, subtract this from this, will give a total number of that. But the key thing for you, not to worry about the calculation, key thing to you is that look at these parameters here and look at this one here. If this number here is very small, then that tells you that you don't have much space, many degrees of freedom left to estimate this number here.
Okay.
Like in our case, we have only 1 degree of freedom in that table. So if you have 1 here, it means that with a sample size of 210 and with all the parameters, you only have 1 additional number that you can, 1 additional person that can leave out from your sample. Here you can leave out, here you can walk around 260 people.
I see. Yeah.
Yeah. So the larger this is, the better for your model. This one is based on what you specified in the model. Okay. They are calculated based on your model specification. This one is calculated based on the parameters and everything else and the sample size. Okay. Hopefully we'll come back to this. So
okay, the
key thing I wanted to note here is that this is a perfect fit. So if you're wondering how should I interpret these measures, this simulated data will give you a perfect fit. So that's one of the reasons why I decided that let me use simulation. My previous courses, I wasn't thinking about simulation. In this course, I was forced by circumstances to think about simulation because I would run models and they don't work. And I couldn't see the literature that helped me. So I said, okay, go back to first principles. First principles say if you simulate, if you don't know anything about what you are doing, simulate a model that will give you a perfect story, then see how it looks like. Then you can use it to compare with yours. Okay, that's the first principles. So I went back there and I simulated this and I noticed a perfect model. What does it give me here? P is almost 1. It's approximately 1. Okay, adjusted is that, but P is about 1. Okay, so I use that as my basis. And the sample size is that. So you go that this is a perfect model. The farther away this is from 1, the poorer your model compared to the perfect model. So if I get 0 here, it tells me that it's a bad fit. It's not a good fit. Okay.
Yep.
So that is the concept there. Then we come here, and this is the first output that I use. If I do, so here now we are testing that there are no effects. So the estimate is that this is 0. Okay, the null hypothesis in all effect sizes is that this is 0. The small p-value means you reject the null hypothesis. Okay, so whenever you look at a test like this, if it is a location parameter, the null hypothesis that this is 0. The p-value says probability that the null hypothesis is true, which means probability is 0. This is a bad way of writing. Normally we should write 0.1 here. We should write less than 0.1, but this is what the software gave me. I couldn't. Normally I modify my software, but just know that this means that it's less than 0.001. This is rounding to 3 decimal places. This is not perfectly 0. Okay, this is not the perfect 0. This just means less than 0.001. So normally this should be interpreted like this. Okay, that's how you should interpret this p-value. That is less than 0.001. This is just a rounding something. So please remember that all of this less than 0.001, which is okay because this is simulated data. We already know that we know that the sample, we simulated data, so we get a near perfect fit. And also my sample size is large enough so that there's no randomness here. Well, there's randomness, but my sample size is large enough to fit the distribution properly. So you have to estimate a standard error and then the Z value. And remember, Z is just the estimate. Since the mean is expected, the expected mean is 0. It's just the estimate divided by the standard error. Okay. Since the mean is approximate, that's what this is. So this column here is just this. And these are the ones that are shown on the unstandardized graph. This one. Okay. So what you find is that when you do your, and it's a graph that I've used, if I don't specify standardized, then what I see in here will be what I'm seeing in here. Sorry, in here. So what does that mean? Okay, this one I put to 3 decimal places. Here, I think around to 2. So let's look at the first path here, which is, you see this 1, this F6. Let's look at F1. F1 is here. So you have 1.26, which is 1 point here, which is 1.257. Okay, and it's showing us here that it's significant. So I asked in the graph to show me that it's significant. So if I have this graph, I don't need to spend time looking at this again. Okay, I don't need to go back. The table is useful, but this graph tells us which paths are significant by putting these stars. Okay, so any point that I see a star, I know that it's a significant relationship. Okay, so this means that this is significant. This is significant within this factor analysis. Where this 0, we need to check the 0 there, but it's a rounding. And this is not significant. Anything that doesn't have a star is not significant. Okay, these ones have been rounded in to 2 decimal places that are rounded as 0. We can check what they are. Okay. So this graph, when I take this graph, you can write the relationships and their significance from this graph. The only thing that you will not necessarily say P is point this, P is point this. These ones are highly significant, as seen with 3 stars. But if you wanted to see the detail, then of course you just summarize and you get that. I'm not sure why you get in M+, but I think it must be very similar.
You're now talking about the loading,
model summary.
Right? The factor load, right?
Yeah. Yeah, remember that here we are looking at, it could be the factor loading, it could be the regression path. They're all the same in this case. No, not the same. From the mathematics, they are giving us the same concept. Okay, so it's showing us at the path factor loading significant. It's showing us all of that here. Unfortunately, I don't know. Yeah, as I said, this is the same style of graph, depending on which one your eyes are happy looking at. This one, if you're looking at just the path, this one looks better because I can see F4, F this, I can see each one of them. It's now the interrelationship that are very interesting. There's a relationship between the factors themselves. Okay. But in terms of the individual factors, this model, this is very clear. This is the same picture, eh? That's the same picture. But here you can see F1 stands out, all its factors are there. I think this one I kept it 3 decimal places so you can see everything the same as it was. Okay. So for the results, when I will look at this, I will look when we look at it, we'll just basically say that yes, all the factors are significant. We expect them because it's simulated data. In terms of what we did, these relationships here, we didn't model this. Okay, we didn't model this. So the model is estimating the relationship between the factors. Is any of them significant? They shouldn't be, and they are not. You don't see any star there. Okay. Now, for the question you were asking, all of these relationships are part of those parameters that are added up to give us the total number of parameters. So you can see that all of these individual paths, which are 26 of them, 25 of them, because there are 25 manifest variables. All of these pairwise paths are still part of them, and the covariances between them are still part of your parameter space. Let's see here. Okay, so what I want us to do from here is to now do some of the analysis ourselves. Okay, I'm not sure you want to take a short break for about, maybe we'll start at 11:30 or 10 minutes break. What do you want?
Yeah, I think we need break.
Yeah. Our 10 minutes break. Then we'll come and we'll download some of the data I'll play with.
Yeah.
What actually we would like is that your data set. Well, okay, because this is structure, let's try to do the confirmatory factor analysis. with a short example. Then we take that your data and we take that your data and then go through it and see. So let's come back in 10 minutes.
Okay.
That would be 11:35.
Okay.
And are we going to 1 o'clock or 12 today?
I presume you have the energy to go to 1, at least 10 to 1.
Okay, yeah.
Yeah.
That's fine. Yeah.
So we can spend 1 hour on the practical side of it.
Yeah.
Yeah. About 10 to 1, let's stop so that we don't go over to your other programs.
Right, yeah.
So when it's about 10 to 1, please let me know so we can just pause. Yeah.
Yeah, so to 1 is fine. Yeah.
Yeah.
Okay. See you in 10 minutes.
Sure. Let me pause. You're seeing my screen, isn't it? Hello?
Yes.
Yeah, great. Okay, so this is the one that I used to simulate that data. So I don't want to take us, you remember I said I copied the wrong place. So I want to take us through how the simulation worked. You don't really need to know simulation in this course, but I think you may find it useful along the way, especially if you are finding challenges with your model. My suggestion is I just simulate the model. I hear in M+ even easier. I was reading about simulation, and it appears that's even easier in M+ than here, even though this is pretty easy. So if you're having challenges, just simulate your model. You can make the sample size as large as possible, and then reduce it to what your sample size is, see how the model behaves. Then it may solve your problem quicker than. You remember last week when I was trying to do the thing on the stock data? When I went and simulated the data, I found where the issues were. Because I now just went and simulated some data, feed it into the structure, and then I say, oh, that's where the problems were coming from. So sometimes you may find it easier, just run simulated data on your model, see what happens, and then you'll be able to diagnose the problem quicker than most other ways of doing it. So these are those paths that I was trying to show you in the notes. I forgot. I copied this part twice. Instead of the first part of the nose should be this one. Okay, so this is what I should have put in the handout where I was trying to put the model. And what does that happen? Yeah.
Could you show again the
model?
No, the name of this code again? I don't think I found it in the folder.
Oh, okay. I probably didn't paste it. Let me go back. I just created this folder now.
And yeah, I mean I don't have it.
I did this. Oh, you can't see it?
It's on the very bottom. Okay, so in this folder, and which one are you seeing? Oh, the simulate PPQ data f.r.
Yeah, no, here.
Okay, yeah. If you go into that, which one are you using?
So this one is the last one. Simulate PPQ data. Yes, I want us to start with that one.
Okay. Yeah.
Yeah.
Thank you.
Yeah. Sorry. Yeah. So this is the one that is in the notes. So
okay.
Yeah, that's the one that's in the notes.
Okay, I'll just copy it. Yeah, okay.
Yeah, yes. Okay. Then so let's come here. So the key thing is that you see, I just write them, it's just straightforward formulas. I just take each path, each of those paths that we're seeing here. Here. Okay. So I just take each of these paths and I put it there. It's just a bit of typing, that's all. 0.761. Where is that? I think maybe I must have rearranged it somehow. Yeah, sorry. So 0.761 times that. I think this a bit rearranged in terms of because I tend to use Excel to do this thing. So I say my variables are arranged in order, whereas here they were not arranged in order. Okay, so I just arrange them so that they start with whatever it is. So this P05 is 0.761. You can see it here. P05 is 0.761. P06 is 0.68, whatever it is. P06 is 0.689. Okay, so I basically just take these path coefficients that I have and put them here. Remember this to generate the data that looks like this. Okay, and there are 6 factors, so I put them. What I didn't put were the you remember that this one evaluating the what do we call it, the the reliability of the measures. Okay, I didn't see the factor there in the model, so I didn't bother putting them there. So once you do this, the command is just to simulate data. Okay, is to simulate data, and then these are just doing some data management. They are not big deal. And this command here is to put it as a blue sky data set, so I can save it and do other things. But you don't need, for this particular case, we don't need it. Okay, so for the demonstration, we don't really need it, but I just did that for that purpose. So let's suppose we're to run this model. Let's just do it together. Run this model. So first of all, let me just run the libraries. Okay, I install the libraries. Yeah, hopefully your libraries are going to install. One of the challenges in using R packages in different platforms is that if you use like here, sometimes is it working? Wow, it shouldn't take that long. Yeah. Okay. So then I basically just run the model. Well, are you able to specify your model like this in similarly like this in M+? Are you able to, if you actually send me a model in M+, I can translate it to a model in Lavin, but I don't know how to do a reverse translation. So if I translate it, then you can be able to see the link between a Lavin model and an M+ model.
Yeah, I can see it right now in the chat, because
Okay.
I have M+ inputs and
oh, great.
The comments. Okay.
Mm-hmm, mm-hmm.
You want for the structure model or
no, anyone, because these are really doing the same thing. The packages are the same. I was just saying that from here, like the one that I sent to you, I sent the one that will come back to for this structure equation model. That was using the Lavin formulation. I hope you're able to translate that to M+. That's what I meant.
Okay, so
yeah.
I will.
That you're able to generate the same data using M+. Okay, we can come back to that. Let's come back to that. So in here, in simulation, there's this thing called the seed, which make it as big as possible. But when you fix the seed, it means that you can replicate the random data similarly by using the same seed. So here I made a large sample size. So let's keep, this was a random number that I made big enough. So keep a big number, but we'll change it and run it for a small data set and see what happens. So I will just run all of these commands here. This is, as I said, just the most important command is this one, line 24. All of these ones are secondary. Okay, so line 24 is the most important. Line 25 just asks you to display the first 5 rows and the first 4 columns. Okay, so the first 5 rows and the first 4 columns, and you see the columns are arranged in the way that they appear here. So column 1 is P04, P05, P06, and P07. So they are arranged the way they appear in the data set. Column names, I want you to show me the column names, is showing them there. So these are just basic data management things. They are not important for what we are doing. If I want to store it as a blue sky data set, then I need to make it into a data frame. And all of this is just deciding the number of decimal places when I'm transferring it. So again, there's nothing to think about there. And if I did that, okay, the head command just again does the same thing. So here, see here, there's no data set there, but if I run this line, then it will convert this to a blue sky data set. So it comes up here. Now, when it's here, it means I can use all of these menus to transform the data set any way I want, to analyze the data, do your factor analysis, anything you want, you can now do it from the menus. That's why I run this command. Okay, if I'm in blue sky, just to get the data, into a blue sky data frame. And you see it keeps the same name. Okay, PPQ, this one. I can now save this data into any form, SPSS, any form that I want, just by doing save as. So in here, these are the various options. See, I have so many options. I can save as SPSS, SAS, Stata, and all of these other formats. Okay, so that's what I normally do. You see, I keep saving as 2 different formats. so that somebody who does not have, who is not using R can use the format they want. So now, what about the model? Remember that normally you already have your data. So normally you don't have to, you don't need to generate the data. If I wanted to take this model and run it, then I don't put parameter because my data is different. This one I was putting here was to simulate. Here, I'm running the model on the data, so I don't put parameter. The parameter will come. The parameter will be produced by the data set, from the fitting of the model. So that's how I specify this same model here. Okay, so F1, F2, and remember in our notes we say this specify a latent factor. So my model is all the latent factor. There's no regression terms in here. That's what we do in structural equation modeling. So this is all latent variables. There are 6 of them. This one, what I did in this data set, it's not this one. That's surprise. Okay. I created categorical variables. Okay. I created categorical variables. I think it's there. And I call them already. You can do that together. Doesn't matter. It's good that it's not there. So I created categorical variables and then analyze the data both as from a categorical perspective and from the normal. So since I don't have that one, I will just run this one only. So once we do the model, anyway, are there any questions? If there are any questions, we can ask as I'm rushing around. I may be going too fast. Are we on the same traffic lights, or have I left somebody in a different zone?
Yeah, I think I'm following.
You're following, okay. So when we come here now, I'm just basically, I've put some various comments here to show what is happening. So in terms of the categorical variable, I've put them here, but we can do them together. So I'm only going to feed the model. I'm not going to feed the model with categories. I'm going to feed only the model with this one. So this is a model we are fitting. So I'll just copy it and go to my feed model. Okay. I'll paste that here. I don't know what happened to my other model that I'm only seeing that. Oh, it's here. Okay. And anyway, let me just put it there and do it. I think I rearranged my work so that it looks more tidy. After I finish doing that, I arrange it. So let me just put this guy here, and I'll feed this. Just copy and pasting and taking this one. So where does it go? It goes in here. That's a model part. And then the data is here. Now you see my data set name is different now, so I have to change it. This is the data set I'm using in here. I think this one is the one that I must have shared earlier. So you must ensure that the data set name that you use is the one that you entered there. So my data set name up here is a PP data 1. So that's the one that I must use. I want to see where I call it data 1. So that's the data set that I must use. PP data 1, where are you? It's here. So make sure that the data set, if you have more than one data set, or if you have changed your data set, make sure that in your command, you are putting the data set that contains the variables you are using. That's a key thing there. Actually, here as well. So you're putting the one that contains the variable you're using. Let me just call this one. We'll just call this one fit, okay? I'll just say fit. Fit normal. So if everything is fine, this should fit. If it doesn't fit, then there's a problem. So I'll click that. You say object. This one is not found. Okay. I fitted the wrong model. This is my model. You see that? So that's the model I was trying to fit. So that's not a problem. So I fit that one. It says something here. Some estimated covariances are negative. Now that is very strange because on this data I fitted them and they were not negative. So it's telling us that some are negative. What is the sample size here? So that is pretty strange. I said I fitted on that same data, and this error did not come. Because you don't want some of them to be negative. Okay. Let's see. It's only one in, but as I said, I fitted this model, did everything, and the picture that you saw there came from simulating that same data. And it didn't give me negative. Let's see where the negative ones are coming from. These are covariances. You see? So you see a variance here which is negative. And the variances cannot be negative.
What does negative variance means?
Exactly. The variance cannot be negative. So in whatever method is using for estimating the parameters, it found a negative variance.
But what does it mean? I mean, in terms of
that what we say is that the variance should not be negative, so it doesn't have a meaning. It's just that there's a problem with the model.
Okay.
Yeah. So there's a problem with the model. That's why I gave that warning sign. So if the variance is negative, then your results don't make any sense. It's like having a correlation bigger than 1 or smaller than -1, and then you are trying to interpret it. It means that the model has not fitted properly. But what's curious is that all the pictures that you saw in the notes are based on this same data generated. So it's very interesting that one moment the computer should be able to fit it, another moment it says, sorry, I cannot fit. It's fitted, but it's not the correct model. Okay.
Okay, I've learned that if the variance is negative, or the fit criteria is not fit, doesn't show the range, I can use the modification and this indices.
Yes, they use that modification indices. That's very true. I think I actually had a line here that I included that, but I took it out. Can't remember where it is, but I did put a line there somewhere. I took it out. I thought it was not useful for us. But the fundamental thing is that it shows a problem in the data and the model that we are trying to feed. Yeah, I put a line. I think I took it out. I had too many codes, and I took that modification indices out. But it's good that you have a solution for that. But the key thing, remember that the variance by definition should not be negative. So it shows a problem with the data. But it also tells you about the method of estimation that is being used. Okay, let me give you one example that will get a lot in statistics. When you do a multiple regression model, the multiple R squared is proportion of variance explained. But what happens is that the multiple R squared will always increase when you increase the number of parameters. So what we have is what we call the adjusted R squared. Now, the adjusted R squared is still supposed to be a proportion of variance explained, but the method of adjustment is such that sometimes you get a negative value. You see that? So sometimes your adjusted R squared become negative because of the method that they have used to do the adjustment. That is something similar that is happening with your variances here. If you compute variance by the normal formula to say is the value minus the mean squared, sum of them up, then divide by n minus 1, you will never be negative. It will be at closest will be 0. But because you are not using that formula, you are using some adjusted formula. That's why we get this sort of number here. Yeah, as I said, the challenge here is that I'd already done this data set and ensured that it was going to work, so that I only exhibit other things and it's not quite work the way we hope. So anyway, from our output, these are just the default parameters that are being outputted here. What do you see? You see that each of these variables has its own parameters, so there are 25 of them, and then we have the factors themselves, which should also have covariances between them. And these are the output as we get. What says here? So this one now are not being estimated. No, they are. The model parameters now are 65 instead of 190 that we saw before. Okay, this one is still 260. So something very funny is happening with the model fit. And it's not a software that I've spent a lot of time on. Yeah, this was supposed to give us something basically the same, especially the number of parameters here and here. It was supposed to give us, where are we here? It gets a bit irritating when So not here. Yeah, this was basically supposed to give us the same sort of result. Okay, because the same data, same simulation, nothing really different. Okay. What I really wanted to do was to reduce the sample size and we'll see what we get. So I was not really, I didn't want to get this negative value. Anyway, let me just check if that data set, the one that was there is this one, I think. The one that was there before. I want to see the data set. Okay. Let me just open that one and see PSIM data. I think you should have this data in the folder. I think that's the one that I shared in the folder. Okay. I think this is the one that I shared in the original folder.
Mm-hmm.
Yeah. So let me run that one. Let's see what happens so that we should get the same result because it's exactly the same data. Okay. So let me run. Now it should be PSIM data. So let's run it here. And see what happens. So we can actually run both models here. Same thing. Okay. So something I'm not sure whether Blue Sky is having some internal issues. Yeah, something I'm not sure. I've had to get out because this is exactly the same data, the same model. So there shouldn't really be any issues there. And it's giving some problems there. So something I'm not sure if the Blue Sky itself has some internal issues. It's a newish package. I don't know if this problem persists in your own M+. Let me see. Yeah, very strange. Very strange. We'll change the name here to feed 1 just to make sure. And this one. Change it to feed 1. Yeah, I'm sorry for that. I wasn't expecting. I was expecting to do something different to show you this and then change the sample size and we'll see the effect. But it's not even allowing us to get the results we're expecting. This variable here is variable 21 that has negative. I want to see what would happen earlier. What variable was that has negative? The same variable 21. So the data are basically the same, even though I've simulated new one, but it's the same as the old one in terms of the parameter here. So it must be something to do with what Blue Sky is internalizing there. Okay. Sorry. Let's look at the next one. Anyway, are there any questions here? I can plot the graph, but any questions first?
Yeah, I don't know if you want to talk about the loadings later, but I have problem in my data, in my models, that I have in some models that I have factor loadings equal to 0.09. So I know it's very high. It's like similar. The variable is similar to the factor itself. So what should I do in case when I got the factor loadings equal to 9?
Equals to 0.9 or
0.9.
Okay. What were you expecting your factor loading?
Yeah, I'm talking about factor loadings.
Yeah,
yes.
so you had 0.9, and what were the other factors?
Around like 0.8, it's around, yeah, 0.8, 0.7, and 9, you know.
So what was it?
Range, like for one model, for example.
That's a confirmatory analysis?
Yes.
Okay, so what was your challenge there? What was your concern? Isn't it want your factor loading to be high, all of them, if you're using a confirmatory factor analysis?
So if it's high, that's what
you normally want, isn't it?
Yeah.
Yeah, if you're doing confirmatory factor analysis, you want your factor loading to be high. Isn't it normally we say that we are taking the factor, if you do rotation, the idea of rotation is such that variables that have low loadings are excluded, variables that have high loadings are included. So, okay, so what is the question in terms of, what is your...
Yeah, I was concerned if it's so high. I didn't know that having high loadings is good. It's a good result. I thought it's
no, that's what you're expecting.
The same of the factor.
Yeah, for confirmatory factor analysis, you want your loadings to be high, isn't it? Isn't it? We arrive at that at the model by let's come here. Actually, that's what I want to do next. Let's just do that next. I want to do factor analysis on this model, if the model had any issue, to see how they compare, okay, to see whether that factor structure is what we are getting. So if the result would say this, so if we're going to a factor analysis, remember that's what I wanted, as I was saying, that let's compare to say if you are concerned about your model, does your analysis show the same factor structure that you are proposing? So let's just do that here. This is only to P, the Q are those ones. Okay, so we do our normal, we can do a screw diagram to say how many factors do we think we have, and we can do our very max rotation. So let's just keep at that. Let's not bother about storing. We can store this later on, but let's leave that and see. So what are we expecting? If we didn't have any statistics to test, we just had our data, okay? So let's suppose you never had any software. You could do your factor analysis and you had your data, and you are told that this is what is expected. Okay. And sometimes some of the things that I say to you is because we studied at a time when we had to write our own program to do most things that were novel. Okay. Most things that we did that were new, there was no software to do it. So you had to know the first principle. So you come here, I'm told that this is a factor solution, and I'm trying to say, do I expect that factor solution? And the only tool I have is factor analysis. I just come here and say, okay, let me do my own factor analysis on my data and visually see how similar it is. Okay, the first thing is to say, are these variables all grouping together, or are some of them jumping to another group? That's the first thing I want to say. And the next thing is that, are there 6 groups? Are there 6 factors? So those were 2 basic things that I say. I want to just look at using my own data. Forget about confirmatory factor analysis. I don't have the package for it. I just have my data. Let me see what my data tells me. Then we'll come in here and we'll do this. Okay. We can also check, remember, the method of estimation and rotation can lead to slight differences, remember? But we saw that when we did rotation, the results were very similar. So also check in the literature what method of estimation and rotation they have used. So let's come here and say, I run this one, and then I see how are my results. Okay. Remember that this is simulated data, so the result will be perfect. Remember, the result will be very good. So what has it done? The variables that we had there, let me just put it back. So we have this one next to us. Okay. So in here, factor 1 that we are seeing, P4, 5, exactly the same ones, because it's simulated data anyway. So this is cheating. Okay, but anyway, confirming what we expect to see. So factor 2, I'm not sure how big this is it's showing us 1, 2, 3, 4, 12, and 13. So let me make this one large. Factor 2 says 1, 2, 3, 4. Do we have any 1, 2, 3, 4 together? 1, 2, 3, 12. Where is 4? Say 1, 2, 3, 12, and 13. 1, 2, 3, 12, and 13. Let's see here. 1, 2, 3, 12, and 13. Okay. Yeah. And the reason why it's working like this is because we simulated the data. You see that? So we've simulated the data without doing any confirmation factor analysis. We just do our normal factor analysis, and this is what we find. Now, what it's telling us, interestingly, is that with this analysis, factor 4 also has loadings in this factor 3. The only difference is that, you see, because we have done a cutoff as well, we've done a cutoff at 0.1. the default cutoff. So it's now showing us factor 4 as a contrast between factor 3 and what was originally factor 4. Factor 4 here was, we can enlarge it. I hope I'm making sense to you. Factor 4 was 9, 10, and 8. Okay, so here we have our 9, 8, and 10. They are still there, but it's showing us coefficients for what is originally factor 3. What's the reason? And then also showing us coefficient, factor of 3 is also showing us some of the coefficients are in factor 4. So you can see that these two factors are showing some correlation.
Yeah.
You see that? Now, we can now decide if you are doing large cutoffs, that means that we change our cutoff points. In SPSS, we just go and say suppress. So instead of suppressing at 0.1, you can suppress at 0.3.
Mm-hmm.
You see that then all of this will disappear.
Yes.
You see that? So this one is because we say we suppress at 0.1, then we are getting this situation here. It's not because the model is different, because we know that this is simulated data, so it's going to give us a factor structure. So if I come here and go back here, anyway, in the question before I go back, let me not enjoy myself and leave you behind. If I come here, where is that place for? Oh, this guy doesn't even provide. Oh, Blue Sky doesn't do it. That's funny. Okay, suppression? Suppression. I'm trying to see where it does suppression.
No.
No, Blue Sky doesn't seem to have it there. But in SPSS, you have that, isn't it? SPSS,
Yes.
you have where you can suppress the distance. But I don't see it here in Blue Sky. Yeah, those are some of the limitations of a package which is new and the package that SPSS we have been around for before what was born. There will be a big difference in what they can achieve. Okay, so we can suppress it. I can't see where to suppress it here. So if you're using Blue Sky, you are stuck with this solution. Okay, and the coefficients are all less, that there's none of which is close to 0.9. Again, it's how they've been rotated. There are some methods of rotation that I said, I don't know if I said it in the notes, like this one. So some of these methods have their own advantages. I think the revised notes is, I think I've said it there. Okay, so did it give that method on rotated? Where's rotated? What does it mean by unrotated here? Didn't I just say it should rotate? Oh, these are the rotated now. Sorry. Maybe I was looking at something wrong. So you see the rotated one here don't have those situations. Okay. Was I even reading the right thing before? Oh, I think I was reading the wrong thing, eh? These were unrotated. So this one were actually unrotated, they just suppress the coefficients. Okay, the rotated ones are here. The rotated one reproduce the structures completely. Okay, I think I'm too used to SPS. When you put rotated, that is when you suppress the coefficient and go. So you said the rotated one, there was no issues like what we had in the unrotated solution. Can you see that? Even the one that I was looking at, you see this one that was interpreting, I was looking at the unrotated solution. Once it's rotated, we've actually captured exactly the same solution as before, as generated. So what about this method? Does it give any substantive difference? Maybe not in this case, 0.4, 0.59, 0.55. 0.4, very similar. No, not this one here. Very similar. So the good thing, as we said before, is that when we rotate, once we get rotated solutions, the solution tend to be very similar, independent of the method. But the key thing I wanted to show you here is that you can establish this solution without doing any tests. Okay, so you take your data, you do your exploratory factor analysis, and you see whether the solution is actually similar to the hypothesized solution that you are generating here, irrespective of the coefficients. Is it what you are getting here similar to this model? Then you already, when there's a failure, you already know where the failure is. You see that? So if you came here and you found that some of your variables, you found here that some of your variables, let's suppose we came here and we did something like this. Okay, let me take this one and put it here. Okay, let's put this one here. Maybe let's take this one. Okay, and put it here. You see what I'm doing? You see the game I'm playing here? This is a game I'm playing. I'm saying this is what my proposed solution factors model is. I did in the wrong variable. I did it in the wrong place. Let me do it here. So I'm just saying, let me suppose that this variable is actually, I'll put it here. And maybe this variable, that's my proposed model. That's my model that in the previous data set, I assume it was. Suppose I did something like that. And maybe even this one here, I put here. Okay, suppose I run that model. And I come here and run it here. I'll call this fit 2. Okay. So solution is still giving the same warning thing, but it's still a warning. So I will still summarize it or even graph it. Oh, so the solution was really not found. Oh, there's a problem with this. There's a problem with blue sky today. There's no problem with fitting that model with the sample size that we have. It should be able to fit the model. There's no reason why it's not fitting it. You just have some ridiculous variances here. What can I do? Okay. I'm a bit disappointed with that data. What can I do here? There's absolutely no reason why that model should not fit. It should just fit and give us a profit. Okay, mathematically, it should give us a profit, but there's something strange going on with the Anyway, let me not take unnecessary time for here. The key thing I was trying to illustrate in that situation was to say, suppose we actually specify a different model. Okay, we simulated that model, all right, but that we have data, and then suppose this is what the model was telling us. If that's what the model was telling us, and before we even run the model, we could do exploratory factor analysis, and then tell us what are we finding from our own data. All of what your confirmatory factor analysis will be matching what you are seeing with your eyes to what you hypothesize to be the model. That's what it will be. Okay, so that's the key thing I was trying to make there. Let me do something different. Let me come here and do something different. Okay, then I'll show you. I will illustrate the point again. I will go here and do factor analysis. Okay. I will take a few variables from here. Maybe let me just take these variables. So what I want to do is just take a few variables from here and okay, And from here to the last set. Oh, okay, those are categories. Okay. Okay, so I have just P4, P5, P16, P17, and P18. So let's come here and propose a model. Let's propose a factor model. So in this model, let's say we want to use these variables, and we think that is a one-factor solution. Okay, so let's just say F1 is manifested by these variables PP045. So let's suppose we just say it's manifest by 5, 17, and 18. 17 and 18. We could just for interest, let's just keep that one factor model and see what it tells us. Okay. So let's suppose we take this one factor model. We know that this is a 3-factor model. Sorry, is it 3 or 2? 2-factor model. So it's a 2-factor because P4 and P5 are factor 2, P16 to P18 are factor 1. So that's why we say it's a 2-factor model. So let me run this and then just sim, and we take that variable, that model, put it in there, and what's our data set? Our data set is the same. So let me copy it from there. I'm minimizing errors by copying. So it's there. So let's hope that this one doesn't give us errors. Okay, so you see, it runs. This one runs without errors. Number of parameters is 8. Degrees of freedom is 2. And it's highly significant. No, it's not significant. See that? So why is it telling us? It's telling us this is not a good fit. Isn't it? It's telling us it's not a good fit. Which, of course, we know is not a good fit because this was a 2-factor solution, and we are saying that's a 1-factor solution.
Yeah.
So it's telling us it's not a good fit. Okay. We can, you say the number of, when I just run like this, the output is limited. So let's store it. FF1 equals to that. So I can now do something more. Is it trying to be funny or something? This is the same model it ran. Or it did say something maybe negative. There's some, this problem is not a data problem. This is a problem of the software. Okay. It's not a data problem. That much I'm sure. As I said, all the demonstration we got was exactly on the same data. So let's just ignore that those is errors and then summarize. Summary, sorry. FF1. So now we are going to get more output. Okay. So we get more output, and what do we find? This variable is not significant. It's just PP5. Where was P05? It was in factor 2. Okay. But I was expecting P04 also not to be significant, except that the model is not behaving properly. Oh, Where's P04? P04 is showing that it's significant in the model, but P05 is clearly not. Okay, so why is this showing here? Unfortunately, the model is not stable the way I was hoping that it would be. I was expecting that all the data here was going to behave well, and we illustrate these points, and you see the strategies that you use. So we're expecting P04 and P05 not to be in the model, not to be in the model with one factor, but it's saying that it can include P04. What if we came here now and say, okay, we think F2 should be P05. Okay. Because from that model, we could easily think that, okay, from these results, we could say, okay, maybe we can take F2 because we have not done explanatory factor analysis. So I come here and say, okay, I'm going to improve my model by taking out F5 and putting there. Of course, it has to make sense. The reason I like your example is that it's based on a conceptual problem. So that's like, I think maybe I should leave this and go there. I like it. It's structural equation modeling, but we could have added something there. What I like is that it's based on this conceptual problem, not a mathematical thing like what I'm doing here.
Mm-hmm.
Yeah, because what I'm doing here is just mathematics. It's just playing the game. And to understand based on playing that game, what happens when certain things change. But let's say we run this and we do this here. Still is having problems with inverting anything. Did they even feed? It's really ridiculous.
You want me to send you the M+ input I have?
Okay, I think I was just thinking about the three of us. Let's ignore this problem for now, and then know that we just look at the result that it's having. Otherwise, we'll have to reinstall. I have to install it and do those. Or you mean that you are doing the same thing in M+?
No, it's not like just the model. I mean, they're running the model.
Okay, you run the same model on M+.
Not this. No, my model.
Okay, no, your model will go to in the next few minutes. Yeah, this game does not.
I didn't do that. No, I didn't do that.
Okay, this model doesn't want us to do it, so I will go to your model in the next few minutes. But let's just see what this summary looks like. I say what is irritating to me is that when I simulated that data, I tested it over and over, and it worked. I say, okay, this is good. We're going to use for teaching, and then I used to illustrate the same points I was trying to make. So what's happened here? So first of all, let's look at the model. Still, despite the fact that we know for sure that this is a two-factor solution, because of the fitting issues, it's not fitting the model at all. Okay, it's not give us. This is a wrong conclusion based on the data, because our analysis shows us clear that it's a two-factor model. This on rotate. Okay, where's the rotated? This was what happened to the rotated? I was reading the unrotated. Let me go back here. Oh, sorry. Yeah, I assumed that he had rotated, he had not. Well, the rotated, you see what's happened? The rotated had, well, no, that is not, where's the rotated? Here. No, but the rotated solution is the same, so it's fine. It's the same. Because they were independent anyway, so the rotation does not change since the two of them were already independent, even unrotated. Yeah, so the main thing is that we know that this is a two-factor model. Okay, and these are the factors. So at the very least, okay, maybe I should put F4 there. Sorry. Before I criticize it, I should put F4. Okay, so where is the other one? F4, 16, 17, 18. Where is 16? Okay. So I'm just taking those ones and putting them here to say this is what is happening with the same data set. Solution has not been found. Very strange. It's even worse, eh? We have a data set that we know fits the data perfectly, but a solution is not found. Oh. Okay, let's I'm sorry it's not it's not allow me to demonstrate the thing I wanted. I might just do it again, and if it works well, I will send you the video. If it doesn't work well, I will ignore it. So let's go to the other data set. Anyway, are there any questions? Any questions on that before I leave it?
For me, no.
Okay. Sorry. Okay. Yeah.
No.
Okay. So let's let me clear this and go to your nice data set. I will close these ones here. I hope it doesn't misbehave now, eh? Did you try running it?
No, because I mean,
You just saw it now anyway, so it's okay. Let me do this.
so these are the simulations, right? I mean, is there like a simpler version, like just, fit some data,
That's
vector analysis, and then feed with some other data and do the confirmatory analysis? I mean,
yeah, that's what I was trying to do there, but it's okay. Let's look at this data
Yeah.
set. Let's look at this. Okay, this one. Oh, do you want to take us through this? Maybe talk to it for us. As I said, I like it because this seems like a real problem. So I didn't have the data, but we could still run it.
Yeah, this is the hypothesized model for my PhD dissertation, and I have 6 variables, and I'm proposing that the relationship between the authentic leadership, the indirect path from authentic leadership to the outcomes, which is interpersonal conflict, job satisfaction, and turnover retention, through structural empowerment and psychological empowerment. I'm not testing mediation or moderator. No, I'm just testing the indirect effect and also the direct effects between the variables. Yeah. Okay. And then in the testing the hypothesis, I run the CFA and structure models. In the CFA, I run separate measurement model for each construct, like separately, because I think I have a very limited sample size, which is 215, so I cannot run the whole model, like measurements model for the whole, because of the parameter will be high, like very much, and so I have just limited sample size. So I decided to like run CFA for each construct separately.
That's great. So in here, what I found, and I don't know if you had time to look at what I said, we'll go through it just now because it's below, is that this one looks like the overall outcome variable.
Yes.
If I interpret this model.
Yeah.
So the overall is to predict turnover, but in between, you can also predict interpersonal conflict, job satisfaction as potential outcomes. And so, although you say you're not doing mediation moderation, typically this would be what is mediating the effects on this right-hand side, isn't it? Because this is what we'll call endogenous variables. So we have 2 endogenous variables or factors here, isn't it? But with respect to this guy here, we also have job satisfaction will also be an endogenous variable with respect to this one here.
Yeah.
You see that? So in terms of what we've been doing, that's why I said I really like this structure from a structural equation modeling. And from what I hear you saying, it looks like there are sub-items for each of these as well. Is that right?
Yes.
Yeah, because that's why I was thinking that if you wanted to, we could just take one of them and put how do we include that sub-item within the same model. So if we decide that there are sub-items here, then I can modify that script to show us how we do it. So we have a complete package now. Okay.
Yeah.
Because each one of these technical will have sub-items. As we say, the model gets very complex when we put the sub-item within this analysis.
Yeah.
So, yeah. So the beauty is that, so, and you said that you're not interested in testing mediation, but you want to test for indirect effects.
Yes.
Okay. So what in your mind is different between testing for the indirect effect and testing for mediation?
It's just, there is not, I don't think there is a theoretical difference, but it's the language that I use in the
write-up
script.
Okay. Okay.
That's
no.
like when I want, like when I didn't propose mediation effect. I proposed this hypothesis, and then I said, okay, there is no like, I'm not saying there's a mediation in
Exactly.
here.
No, I get you. I get you. So, and that's where you, the experts, come in. You remember what I was doing there? I tell you, I was just playing a mathematics game, but here you are doing a proper analysis, which is where we really want to be. Want to do a real analysis like this. So you're not using mediation, even though you're looking for indirect effects, but you're not coaching in the language of mediation.
Exactly. So
Yeah.
because
Yes.
it's the language. It's like I can like make it another level of this analysis and introduce mediation, but I'm still in the level of indirect and direct path.
Yeah. So let's just go down and look at just this model. And I said I took this model, and all I used was, we didn't know the magnitude, but for me to simulate the data, I put some magnitude values. The key thing was the signs. Okay. I actually wanted to do something else. Then I said, okay, why don't you do simulation model? I wanted to actually generate multivariate data representing this. And I created a correlation method. I said, no, let me go and use this method. So that we are staying together. We don't do too many things. So when I did that, I said I used the signs. And what I did here was to reproduce. I will see that it's reproduced. This is the graph that I'm using. And you see all those effects. So now, without doing anything else, if you fitted that to your data, then this will be what you get. You not the coefficients, but you find that at least it's consistent with the signs what you were expecting, isn't it? I think the signs are consistent when I look at that. I don't think I'd look at them one by one, but I think they're consistent to say this will be a direct effect of authenticity on psychological whatever it was. Okay, so this will be direct effects, isn't it?
Yeah.
Now, every arrow here is technically, from a statistical perspective, a direct effect. It could be a conditional or unconditional, but technically they're all direct effects. The indirect effect is normally measured by taking the products. If I want to say the indirect effect of, first of all, we're measuring, if I'm taking this variable as my outcome and just my predictor, then I'm saying what is the effect of authenticity on interpersonal, whatever relation, or whatever it was. The indirect effect is through psychological
empowerment. Yeah.
Empowerment. So the way that the normally compute that indirect effect is to take this time this. Isn't it? That's the way we compute the indirect effect, is to take this time this, because this one is not the indirect effect of this. So the way that the indirect effect is normally estimated is to say I take this time this. And then I want to take the indirect effect of this, I take this and this as my outcome. The indirect effect on this path will be this time this. So that's the way that is normally they normally estimate it. But most of the time they do indirect effect just on two levels. The 3 levels and even 4 levels that we have here is not often, but it's still interesting.
Okay, I have a question here.
Yeah.
What if the path from the direct path from authentic leadership to psychological empowerment is significant, and but the path from psychological empowerment to interpersonal conflict is not significant?
Exactly.
What does that mean? Exactly.
So it's a product that we evaluate, and I will put the product here. I will show you how we do that product. So usually that's why a package like the structural equation modeling package become useful. And Lavant, I found it very good because it allows us to compute and test for the significance of that factor. Whereas without using a package like Lavant, we cannot test it, because just multiplying it, we cannot multiply the standard errors. And remember that for statistical test we must do. So Lavant gives us that function for specifying and testing that effect. So you've asked exactly the question I was hoping that we can use that. What if one of them is not significant? Then what is our conclusion? We can test it now to see whether the overall effect is significant or not.
Okay. And plus gives me this exactly the question. It gives me the significant path from authentic leadership to psychological empowerment, but not significant
overall.
direction. So how I interpret that is like there is no direct effect between authentic leadership and interpersonal conflict.
No, that's why we'll just do it now. We'll do them now. See, we don't have much time. We'll just go and do that. Okay. What I want to show here, which you can read, is I want to show the standardized and the non-standardized measures. Okay, I want to show that you can compare. This one's a mean-centered, normal, standardized. So this one and this one are the same. So I was comparing this one with your categorical variables to say, okay, if the data were categorized, then how would the model look like? And it was quite impressive how similar they were. Okay, I'm going to show you what I mean here. But let's go and do that issue so that we don't have a lot of time. I've been postponing for too long. I think it's time to do it now. So we'll just take one of them and then do it. What happened to, okay, it's here. So open, I think this is yours. Okay, and now also open the data. We could even shorten the model. We don't need to do the whole model. Let's just shorten the model, then the model I want to fit, and then we'll do that. So you see here, the reason I put those coefficients here is to allow me to estimate the indirect effects or to estimate any effect I want. Okay, so let's suppose we now want to find, let's focus on this one. Let's take, I think you are better off than me to tell me which one we should take. So tell me which indirect effect you want to factor on. So let's say we want to do indirect of structure.
No, authentic.
And
interpersonal conflict.
So I'll just put it like that. And which is the middle variable?
Psychological empowerment.
Okay, so authentic is, do I have authentic here?
Yeah, you have in first line.
Here? Oh, here.
Yeah.
Okay, yes. So authentic is this one. So the path now from, I need to see that graph to do the correct thing, to make sure that I'm, maybe, no, let me close this one. Let me use yours even. Your graph is a better graph. Normally, when I want to do that, I want to jot it down so I'm seeing what I'm talking about. Okay. So we are here. And you want today, you say you're taking this part, is it? Interpersonal.
Yeah.
So interpersonal, so it's here. Oh, this thing. Okay. So interpersonal, I think I'm getting irritating. Let's look at the coefficient anyway. So this is a line, I think. Isn't it? This is the line we're talking about. Interpersonal. Okay, we can take to psychological, it's fine. So let's take that line. So the indirect effect now is the product of those coefficients. Okay. So it's the product of the line from, yeah, let's take this too. So the line from here to here is A. Okay. Then there should be a line from the second variable to here. So it's B. Okay. So it's B1. So that is the indirect effect. Okay. So we'll put a column here. So that's how we test for that indirect effect. And we'll put this level will compute it for us. We can put about the direct effect, or we didn't compute the direct effect here. So we cannot do a total effect. You see, this model does not have the direct effect, isn't it? I mean, from here to cycle. We didn't include it.
It is, yeah, there is a direct.
Well, I'm saying that there's no line. I didn't put any line from here to here, which is a direct effect.
Yeah.
But we haven't put it, or we intended to put it. You are not.
I didn't put in this, but I put it in the structure model.
Is that right? Okay.
Yeah.
I didn't put it. No, one says that this model that I specified here doesn't include that one.
Yeah.
See, it doesn't include, this line is not there. If you look at my path doesn't include that line. So I don't have a parameter for it in this model for the direct effect. So if you wanted the direct effect, you see here, there's no parameter for it.
Yeah.
So if you want me to put a parameter, then I have to put that cycle. If you want me to put that now and then do it, then I will put here cycle equals to let's say C times authentic. So that will be the direct effect that I'm doing. Okay, so I'll come here and say direct AU to IN equals to C, and then the total is now your direct plus indirect. Okay, C plus. Okay, you just put the two of them, A times, it doesn't matter where you put the bracket or not anyway, B1. Okay, so you can do this, and let's hope that it doesn't misbehave again because it was working just so nicely yesterday. So if I run that model, if I run the model, okay, then let's go here. What's the name of the model? So the key thing is that you should see how to specify those effects. Okay, so you take the path, specify them, and then run your model. Then it will estimate them. Now we'll use bootstrapping method to estimate. So that's a good thing about it. Where's my model? Okay, it's here already. What? Duplicate model, what does it mean? Oh. Okay. It's complaining here. Yeah, not to worry. It's complaining here. So if I want to do that, I should take this one out. Okay, that's why it's complaining. So I want to do that, I should take this one out. Okay, because say it will do the same model, but now I've taken one out, so there's no duplicate there. So cycle is this, cycle is this. Okay, so let's see if that is why it's complaining. So it's just as well we did that and try to run. Where am I here? Here. What? Oh, P1. Oh dear. You know, you see why teaching packages, we try to go to menus, because when you are teaching, you don't really have time to making typing errors, and then you keep complaining. And so you say B1. Okay, because you say I deleted B1. Where is it here? This one. So it's B2. So it's just as well that I deleted because I was using the wrong thing anyway. I was using the wrong, what the coefficient I was using was wrong to start with. So it's good that we made that mistake. You said the coefficient I used before was wrong. And remember I told you that I tried to put each equation on its own line. This is an example of how to avoid the errors. When you put each equation on its own line, it's easy to see what you are combining with what. So
also there is a B1, you can put B2 in the indirect occasion. Yeah.
Okay. One B2 as well.
There, yeah. Here, I mean, indirect path, indirect line. First line, indirect line.
Oh, thank you. Yes. Thanks. So it's B2 there. Yeah, it's good to have two people looking, you know. I will spend 5 minutes wondering what the error is. Okay, let's see if everything is fine now. Here, let's see. Okay, run where? So let's see the model. I've been talking about showing you put this one. So it's just as where the opportunity presented itself. So you see them, they are here.
Yeah.
And not only are they there, the most important thing is not that they are there because you could compete by hand. The most important is that you have a test for them. So you tell them that they are significant. So that's how you test for your, the key one is what? The indirect effect, because these two are already, this one is there, the total was not there. So now the total and the indirect can be tested. This one should be up there already. We know that this one is a direct effect from where some, just name them in such a way that you know what they are. But this is a direct effect from, we say from what? Can you see the parameter up here among your direct effects? This was A. So A is there. Was it A? No, it was not A, it was C. This is it. Okay, so it's not changed because we've not done anything. It just copied it and put it there with the same test statistics. What has changed is that it's computed this one and tested it, and it's computed this one and tested it.
Okay.
Yeah, that's the key. That's the key thing. That is actually, if you do path analysis, for me, the most important benefit is this aspect of it. Is whether these effects are significant or not, and you are doing a proper statistical test on them. Okay, and these are using Bootstrap. So Bootstrap is easily the most powerful thing to use when you don't even know the distribution of the parameter. Then the Bootstrap helps you. How does it work? The easiest Bootstrap is what they call the leave one out. So leave one out means I have 1,200 observations. I take one observation, I'll feed the model, estimate, take the next one, put it back, take the another one until I do 1,210 times. Then that sample I used to find this estimate, which is always going to be the same as the true one. Then I find a standard error based on that sample. So it's a sampling standard error. And then I do a test. I assume normality and then test to see whether it is normally or not. So that's what the Bootstrap does. Other Bootstrap would divide the sample because that leave one out can be very time consuming. Other Bootstrap would divide the sample, say I have 1,200. It divides and say I want to have a sample of 10 each. So that means there will be 121 samples because there are 1,210. So there are 121 samples. Then divide by 10, so 121. So it does 121 estimation, find their standard deviation, use that standard deviation to test the hypothesis for normality. You see, so that's what Bootstrap is doing. So it's not even, it doesn't care what distribution you are. It just is able to feed that over and over and over and then give you this estimate. So that's the beauty of this function to do your estimation and do your test of hypothesis. Okay. So if you are doing structural equation modeling, I suggest that you take the path and you write down this. And the easiest thing I found, as I said, is what I was doing here. That each path that I want, I put it separately. So normally I don't put like this. I put them separately that I was doing here. Okay. So I just took only one path. So you'll see that if I'm going to do this type of thing here, I don't put two lines because we'll get confused and sometimes when you put two lines. But I still use the symbol like this. So I look at the path and I say this path is from structure to this one. I may put B1 or A1, then B1, A2, B2, and so on. So when you do that, it's easy for you to write all of this out. Yang, are you with us? Is the example making sense to you?
I'm not sure, really.
Okay, let's go back to what we're trying to do. So this is a real life data set or a real example, a practical example of a problem. And you see the way the problem is coached in here. And this is, at this stage, we have only done the structural equation. We are not doing the factor analysis in this model. Okay, so we are assuming that these are already measured as they are. So we're just doing a structural equation modeling and look at the various paths. The issue is that how do we get these various paths into our model? Because that's really what's important. Okay. So how do we get these various parts into our model? Forget about the simulation. If I want to get the various parts into my model, what I did before is to take, remember that the outcome variable comes first. So structural is the first line that I'm focusing on.